gravity, atoms, and light. These are essential components in rendering the universe as we experience it today. Both on Earth and out in the stars, we see a wide variety of physical processes and reactions responsible for making things happen in space. But all of them can be boiled down to just 4 fundamental forces of nature, which wrote the laws of physics during the earliest increments of time. Gravity is one of these fundamental interactions, while light makes up part of another. And by understanding all 4, we can gauge comprehensive insights into the true workings of our reality, from its tiniest particles to its largest galaxies. And in this video, we'll be doing just that, unravelling the mysteries of the forces of nature, examining their behaviours, origins, and their overall effects on the young universe. It's a wild ride that'll take us all the way back to the beginning of time. So get ready as we immerse ourselves in the essences which bind the cosmos together, the 4 fundamental forces. As mentioned, there are 4 types of fundamental interactions implementing the laws of physics in the universe today. Most evidently, there is gravity, the mysterious force of attraction holding together the cosmic web and keeping celestial objects such as planets bound. Then there are the 2 nuclear forces, one which glues atoms together and another which breaks them apart. And finally, we have electromagnetism, the palette painting the universe with a plethora of radiation, including the visible light illuminating our everyday lives. Together, these 4 forces facilitate the breadth of interactions playing out in space, each mediated by their own type of elusive, force-carrying particle known as a boson, a messenger particle which acts as an agent for its force's behaviour. The well-established and rigorously tested standard model of particle physics, the science found in textbooks, classrooms and libraries, describes bosonic particles for 3 of these 4 forces, the 3 gauge forces influencing atoms in the quantum domain, for which we have a wealth of understanding. But when it comes to gravity, the standard model comes up short, offering no explanation for its mechanisms. For that, we must turn to Albert Einstein and his 1915 general theory of relativity. This set of rules and equations, which stands out as his grandest achievement, informs the basis for our modern-day understanding of gravity, and it has passed many empirical and laboratory experiments. The problem, however, is that relativity is a classical theory, and not a quantum mechanical theory which can tell us about the behaviour of particles. Rather, Einstein modelled gravity as curvature waves within a field of mass, never explicitly invoking a boson to carry the gravitational force. And though this so-called graviton particle is believed to be lurking out there somewhere in the background of space, it has never been observed in practice and is invisible to the majority of Earth-bound experiments. As a result, no one has yet been able to reconcile the behaviour of gravity on a particle level to those of the 3 gauge forces given by the standard model. To do so would be to unify 2 at-odds areas of science in a grand, overarching theory of everything, which can mathematically explain the nature of all 4 fundamental forces concurrently. In the meantime, however, the field of quantum gravity, or how it works in terms of particles, remains one of the major sticking points in modern cosmology. Indeed, gravity is the most elusive of the fundamental interactions, whose mechanisms are shrouded in secrecy. Despite being the weakest force by far, it still maintains the widest reach and greatest range. Neither does it require anything fancy to get it going, such as light or heat. All we need is mass. Mass invokes interactions with the gravitational force, and thus if you have mass, you have gravity. As such, it has played an outsized role in sculpting the universe for almost 14 billion years, ensuring the stability of space on the largest scales. And yet, its workings are plagued by enigmatic contradictions and unanswered questions, which cast doubt over our most basic assumptions of the force. On local scales, some 85% of the mass calculated to be required for building up galaxies and galaxy clusters is missing, thought to owe to an invisible, undiscovered particle known as dark matter, which has been seen acting as the skeleton of space but has never been observed directly. And then, on macro-universal scales, where gravity has been the dominating force for billions of years, it now seems that that is no longer the case, as the cosmic web is being pried apart at an accelerating rate by a strange anti-gravity component of the force nicknamed dark energy, which has also never been conclusively identified. These contradictions, along with the apparent absence of an associated boson, leave gravity as by far the biggest outlier in our understanding of cosmology. As a result, we cannot resolve its origins in the very early universe to the grand unified force it was born with. As mentioned, the three other gauge forces, electromagnetism and the two nuclear interactions, can all be explained using the science of the Standard Model. And if they each have a shared science, it's likely they may also have a shared nature, as distinct extensions of the same overbearing progenitor force. If this is the case, then there should be an arbitrarily high temperature at which the gauge forces would unify their behaviours, with particles of both matter and light so greatly energized, their distinctions literally melt away, yielding a grand unified force handling all three types of particle interactions. Such temperatures would have existed only just after the birth of the universe, when it first assumed a finite size and temperature. At time zero, the infant cosmos would have popped into existence resembling a singularity, with all the contents of the modern-day universe compressed into an area orders of magnitude less voluminous than even the smallest subatomic particles, burning at Planck-scale temperatures. But barely a fraction of a microsecond later, the microscopic universe was expanding and evolving, its contents cooling as they were spread over a continually increasing volume. And merely 10 to the power of minus 43 seconds after its inception, the temperature of space had fallen to some 10 to the power of 32 Kelvin, the point at which things started to happen, as the fundamental forces were the first to establish themselves during the boot sequence of the Big Bang. In the beginning, there were two fundamental forces. One was gravity. As mentioned, we cannot resolve its nature to the Standard Model, and so we cannot be sure whether there exists a temperature energy at which its behaviour would unify with the gauge forces. Either way, however, it would have been at this point, during the Grand Unification Epoch, where gravity emerged as its own distinct force, which immediately settled into the background of space, leaving only its counterpart, the electronuclear force, to dominate the behaviour of the young universe. If such a force existed, then it would likely have been mediated by its own type of bosonic particle, hypothetical X and Y bosons, the true so-called God particles of the primeval age. Very little is known about their properties or the role they would have played, but they soon disappeared in any case as they were harvested to make way for more conventional bosons, like the Higgs boson, as the grand unified force became unstable. Just 10 to the power of minus 36 seconds after universal inception, its temperature continued to fall below 10 to the power of 28 Kelvin, apparently beneath the unification energy required to merge the gauge forces. As a result, the grand unification epoch of the universe drew to a close as the electronuclear force split via a process of symmetry breaking, yielding two new, distinct forces: the strong force and the electroweak force. Though the grand unified force remains an elusive theoretical concept, the basis for an electroweak force, bridging electromagnetism and weak interactions, was put on solid scientific footing in the 1960s as one of the key revelations in establishing the contemporary standard model. It decayed from the electronuclear force to kick off the Electroweak Epoch of the young universe, setting in motion a chain of events that would leave it unrecognisable by the turn of the next era. As the essences of gravity, strong interactions, and the electroweak force swirled, their coexistence gave rise to a so-called vacuum pressure field, which unleashed a radical resizing event on the microscopic cosmos, slingshotting it en route towards the immeasurable volume we know of today. Starting at 10 to the power of minus 33 seconds after time zero, the primeval universe was scaled up by at least a factor of 26, like stretching a nanometer to the length of a light year in just a fraction of a second. Culminating at 10 to the power of minus 32 seconds on the clock, this cosmic inflation completely transformed the young universe, while also cooling it further to a more modest 10 to the power of 22 Kelvin. At this point, the mysterious energy field powering inflation subsided before decaying into a sea of energy, where the events associated with more classical descriptions of the Big Bang theory ensued. And by 10 to the power of minus 12 seconds of time, this inflationary energy had condensed into a plasma, containing the universe's first particles of matter, known as quarks, intersected by gluons, the mediators of the newly awoken strong nuclear force. The strong force is the second of our contemporary fundamental forces, coming into effect only just after gravity in the events of the early universe. As its name implies, it is by far the most powerful of the forces, a whopping 10 to the power of 38 times stronger than gravity, in fact. But there's a catch, because the strong force only operates over a very limited range of distances, on microscopic scales of 1 femtometer, the typical size of an atomic nucleus. Indeed, the strong force is the glue which holds together the cores of atoms. Whereas gravity is the large-scale force of attraction, strong interactions hold nature together at an atomic level, ensuring the key components of our bodies neither dissipate nor collapse into something denser. Within the nucleus of an atom, subatomic proton and neutron particles are glued together by the strong force, mediated by the gluon particle under a grip incomparably tighter than gravity's, forming the bases for a wide variety of exotic substances, including the many elements and metals of the periodic table. On scales larger than a nucleus, the strong force is an attractor, like gravity. However, at smaller scales and even greater compressions, it switches roles and begins working as a repeller, as subatomic particles packed too tightly yield a degeneracy pressure by agency of the strong force. This ensures the hearts of atoms neither break apart under any reasonable force, nor compact so tightly that their structures are lost as they merge. It is also the same phenomenon holding up the cores of neutron stars, as huge quantities of neutron degeneracy pressure prevent the mass of up to 2 suns from collapsing completely into a black hole. Protons and neutrons, these core constituent particles, are both types of hadrons, whose internal structure is an aggregation of 2 or more quarks, the primordial elementary particles we discussed earlier, which are bound by the strong force. Around 10 to the power of minus 12 seconds after the birth of the universe, the quark epoch commenced as the first pixels of matter began appearing in the ocean of plasma. And over the course of the next second, these quark particles would be mediated by the strong force into aggregations of hadrons, the original building blocks in the universe's first atoms. But before they could get started, another event of symmetry breaking would see the 4 types of interactions as we know them today established. Once the temperature of space fell below a quadrillion Kelvin, the electroweak force broke apart, giving way to both electromagnetism and the weak nuclear force. The weak force is the second type of nuclear interaction influencing atoms and particles. But unlike the strong force, which builds them up, the weaker force is the force of decay, as structures are broken apart to yield new particles and energy. As implied by its name, this force is significantly weaker than its counterpart, and operates over an even shorter range. This is because the weak force is mediated by W+- and Z0 bosons, all of which are dozens of times more massive than a proton, severely constraining their range to just 1/10 the width of an atomic nucleus. And yet, they are the catalysts in some of the weirdest, most wonderful and important physical processes playing out both right here at home and out there in the stars. The weak nuclear force is the only one capable of changing the so-called flavour of elementary particles, converting them in processes such as beta decay. 2 of the best known weak interactions are beta- decay, when a neutron is broken down into a proton, electron and antineutrino, and beta+ decay, where the roles are reversed, as a proton gives way to an electron, a positron and an electron neutrino. If that was hard to understand, just know that this ability to transition the fundamental building blocks of nature to their various other types and states gives the weak force a hand in all manner of natural processes, from the fission occurring in power plants on Earth to the fusion occurring within the cores of stars. Though the majority of our Sun's activity owes to the strong force, the weaker force is still tasked with initiating the critical first few steps of the proton-proton chain reaction powering the fusion of Sun-like stars. And for much larger stars, the weak force plays an even bigger role in the carbon-nitrogen-oxygen cycle, where decay facilitates the synthesis of heavier and heavier elements. Then, when these stars explode in a great supernova, the rapid neutron capture process floods the cores of surviving atoms with unprecedented numbers of neutrons by agency of the weak force, to yield the heaviest metals in the universe, even more enriched than iron. Speaking of supernovae, one of the weak force's most elusive clients, the neutrino, also takes centre stage during these stellar explosions. When a massive star's outer layers collapse, they compress the core until it ricochets against neutron degeneracy pressure. But this alone is not the cause of the tremendous explosion. Rather, it creates the extreme environment in which neutrino particles step out of the shadows to start interacting with normal matter, as they deposit a small portion of their abundant energy to supercharge the star's bouncing layers, catalyzing the superluminous explosion which precedes the formation of a black hole or neutron star. This demonstrates a clear, physical link between the fundamental forces at the highest rates of energy. Ordinarily, neutrinos barely interact with normal matter, floating around like ethereal ghost particles in the background of space. But at excessively high temperature energies, like those found in a supernova, these particles do begin interacting with ordinary matter, implying a physical link in their nature somewhere much higher up the chain, under the most extreme, energized conditions. The conditions of the early universe following the end of the quark epoch. About 1 second into the universe's life, following the partitioning of the electroweak force, newly formed pairs of hadrons and antihadrons latched onto one another and annihilated themselves, allowing the newly established weak force to convert their byproducts into a second type of primordial elementary particle, leptons. A class featuring electrons, muons, tauons, and neutrinos, none of which exhibit strong interactions ordinarily. But during the Lepton epoch, the temperature of the young universe would have been so high that both types of nuclear interactions would have affected these newly formed particles. But as another second of cosmic time ticked by, the temperature of space dropped further to below 1 billion Kelvin, the point at which neutrinos were able to decouple their behaviour from ordinary matter, and sink into the background of space as the ghostly essence we know them as today. Such a decoupling event would have no doubt etched an irrevocable imprint of its final interactions with matter into the fabric of space itself, analogous to the cosmic microwave background, which is currently our earliest snapshot of the young universe. But the CMB was formed when it was almost 400,000 years old. Just imagine the mind-bending secrets we could unearth if we could capture this cosmic neutrino background emitted just 2 seconds into the universe's life. Such a profound snapshot would completely revolutionize our picture of the primordial cosmos. Unfortunately, however, even at the best of times, neutrinos propagate with a very low rate of detectable energy, and their experiments are vast, complex, and expensive to construct. But for the universe's oldest, coldest, and lowest energy neutrinos, it's a different story entirely, far beyond the realms of feasibility in any of our lifetimes at least. As such, this tantalizing map of the infant cosmos, and the smoking gun that would all but verify everything we've discussed so far, will likely remain hidden forever, teasing humanity from the shadows. For now, our earliest view of space is the aforementioned cosmic microwave background, the oldest detectable signature of electromagnetic radiation, which was emitted when the universe went dark. The final fundamental interaction, and the last to establish itself, is the electromagnetic force, whose agents began dominating the universe's behaviour at the end of the Lepton epoch, about 10 seconds into its life. Though not quite as powerful as strong interactions, electromagnetism still wields considerable power, responsible for a broad range of energetic processes as a result, including the emission of visible light that we can see. It works by instilling particles with an electric charge, either positive like a proton or negative like an electron. This charge property then elicits interactions with the electromagnetic force as a region of influence is created around the particle known as an electrostatic field, which facilitates interactions as opposite charges attract one another while like charges repel. The movement of these charged particles then gives rise to a magnetic field, as a distinct yet closely related phenomenon. Electrostatic interactions are the final layer of glue holding together the structures of atoms. Beyond the nucleus, where the strong force has no bearing, these currents keep charged electrons in orbit, as the final piece of the atomic puzzle. They also enable the binding of much larger, macromolecular aggregations, like proteins, which are of course an essential component of life on this world. Moreover, the force plays a part in just about every technological process unfolding on Earth. Not just in generating, transforming and distributing electricity, but also for internet services, radio transmissions, and most kinds of navigation, all of which are delivered through the carriers of the electromagnetic force, the photon. Photons are among the most profound type of force-carrying boson, because unlike the nuclear mediators, they are not confined to short, subatomic ranges by their mass. On the contrary, photons are said to be massless, with no tangible weight or quantity to hold them back or limit their interaction. Instead, photons zip around the cosmos on all scales at the fastest speed attainable, 299,792 kilometers per second, or about 186,000 miles per second, aka the speed of light. But it is not just the speed of light, it is the speed limit. As the propagation speed of both gravity and electromagnetism, it is the processing speed of space itself, a hard limit which can never be breached. Anything that has mass can never reach this ceiling. To accelerate to such a speed and maintain it would require an infinite amount of energy. Alas, photons are said to be massless because they're the opposite. They have no quantity capable of holding them back, and so shoot around space indefinitely until they are absorbed, never slowing down in the meantime. By themselves, these massless photons don't do very much, and are invariably part of a much more significant aggregation of light particles known as an electromagnetic wave. And taken together, it is the frequency of these waves and intensity of their constituent photons that determines the type of radiation according to the electromagnetic spectrum, making up the palette painting the cosmos, from low-energy radiostatic to cancer-causing gamma radiation, with the visible light that we can see strung somewhere in between. At the far end of this spectrum, where waves of photons are at their lowest frequencies and thus longest wavelengths, we find the radio spectrum. These are aggregations of photons so infrequent they cannot be seen as such and must instead be listened for. This makes them a useful, virtually harmless tool for transmitting encoded information, which gives radio signals a critical role in our everyday lives. Humanity has been tuning into radio broadcasts for well over a century, while many parts of the world still use it to distribute television signals. Furthermore, radio photons are much less prone to atmospheric absorption and poor weather conditions, making them the medium of choice for satellite communications. The GPS navigation system, which is essential for most maritime, aviation, and even domestic endeavours, relies on radio signals passing between space and the ground, not to mention all the other invaluable services that satellites deliver. And of course, there's the field of radio astronomy, which emerged in the 1960s and has unveiled seismic revelations about our cosmos ever since, from the nature of neutron stars to the noise left over from the Big Bang itself, the aforementioned cosmic microwave background. This static signature of space can be found at the slightly higher frequency shorter microwave bands of the radio spectrum. Microwaves play a similar role in many communications and satellite technologies, but their slightly higher tendency to be absorbed also makes them effective weather mapping agents. Microwaves are also used in medicine, from radar-based cancer detection to the coagulation of the cancer cells themselves. They even have a number of domestic uses. Perhaps the most well-known is in the kitchen, where mini microwave convection ovens heat and defrost food by vibrating molecules of water from inside. As wave frequency increases and wavelengths continue to shorten, we soon reach the boundary of the radio spectrum, where we then cross into optical wavelengths, featuring radiation that we can see. Our first stop is in the infrared bands, an in-demand range of frequencies right now as the James Webb Telescope searches the skies. Infrared radiation allows us the opportunity to study some of the very deepest, darkest corners of space, so distant that their visible light has faded from view and been shifted into the infrared bands by the gradual expansion of space. Therefore, infrared frequencies provide us the perfect channels for bringing the most ultra-distant, ancient galaxies into view from the periphery of the cosmic horizon, enabling Webb to snap ultra-detailed, high-resolution images of the most remote reaches of space. Closer to home, and the brunt of luminous emissions return to visible wavelengths, the next step up on the optical spectrum, featuring all the frequencies that can be seen with the human eye. Visible wavelengths are themselves a mini-spectrum of 7 distinct colours from red through to violet, with all the possible colour combinations intersecting in between. From the light of the sun and the moon, to the bulbs illuminating your home, and even the screen you are watching this video on, visible light dictates how we interface with the world around us, to give the electromagnetic force arguably the greatest influence over our everyday lives. Lighting our streets and motorways and powering our homes and buildings, its role in electricity is essential to the continuation of life as we know it, second only to the sunlight sustaining the Earth's natural cycles. Speaking of sunlight, if we continue to compress waves of visible light and increase their photon frequency, we eventually exit via the violet end of the visible spectrum and cross into the aptly named ultraviolet bands. UV is the strongest type of optical radiation and the most pervasive form found in sunlight. Like other types, it comes in a handful of frequencies, each with their own undesirable effects on the human body. UVA is known to penetrate skin and degrade DNA cells, potentially accelerating the development of various forms of cancer. UVB, meanwhile, is the pesky culprit responsible for sunburn. The strongest, shortest wavelength type, UVC, poses the greatest risk to life on Earth, but the vast majority emitted by the sun is absorbed by the planet's protective ozone layer, a shell of molecular gas which is constantly forming and being destroyed under the glare of the sun's emissions. As such, variances in this layer's thickness often follow patterns in seasonality, latitude, and solar activity, with depletions always temporary to be preceded by a period of recovery. However, it became apparent in the 1970s that humanity's actions were damaging and degrading this protective shield well beyond any natural explanation, as a huge seasonal lapse in ozone molecules took shape over Antarctica. The culprit was quickly identified as compounds today known as ozone-depleting substances, which include CFCs, HCFCs, carbon tetrachloride, and methyl chloroform. emitted by both industrial and household appliances, these compounds then spend between 2 to 5 years rising into the atmosphere, where they are broken down by the sun's radiance to yield chlorine and bromine atoms, two natural killers of stratospheric ozone. A single atom of chlorine alone can destroy up to 100,000 molecules of ozone before it exits the atmosphere, prompting numerous countries to restrict the uses of CFCs to prevent further depletion. And from the 1990s heading into the new millennium, trends in ozone depletion did indeed begin to stabilise, including around the seasonal Antarctic hole. But this hole has never gone away, and did not heal itself contrary to popular belief. Ozone depletion continues to be a major worry for humanity to this day, not least because these harmful compounds are still being used around the world, as new applications for them have been discovered. It just underlines the importance of modernising our technology, to ensure our future practices do not upset the Earth's delicate natural balance. Staying with the subject of modern technology, at wavelengths hundreds of times shorter than UVC, we exit the optical bands and stray into the realms of high-energy, ionizing radiation, strong enough to strip atoms of their electrons, resulting in all sorts of problems for us fragile humans. Our first stop is X-rays. Also known as Röntgen radiation, X-rays are a well-known set of frequencies with a unique place in both medicine and culture alike. Though hazardous in high doses, X-ray photons can penetrate softer materials and pass through them, though they are still absorbed by harder substances. This makes them ideal for making cross-sections of the human skeleton to analyse bone breakages, among other deep-rooted ailments. And their ability to ignore softer materials gives them additional uses in archaeology, geology and agriculture, for studying rocks, soil, water and air. But given the risks posed to humans by ionizing radiation, their usage is tightly regulated in most parts of the world. And for radiation even stronger than X-rays, it's a different story entirely. Gamma rays are the most energized type of electromagnetic radiation, orders of magnitude stronger and shorter in wavelength than X-rays. Their photons so densely concentrated, in fact, that they can pass through the space between atoms in a mirror, and thus cannot be captured or reflected. Unlike other types, gamma rays are only produced by the very hottest, most energetic objects in the universe. On Earth by lightning, within nuclear reactors, and during nuclear detonations. In space, meanwhile, they are spewed out in enormous quantities by supernovae, neutron stars and black holes, the gamma ray sky ablaze with the most luminous phenomena in space. If we could see gamma rays the way we see visible light, our night sky would constantly pulse and flash with luminous mounds, most of which would stream from galaxy clusters billions of light years in the backdrop. In the distant, younger universe, gamma radiation gushes from quasars, among other types of active galaxies, whose central black holes host accretion disks that burn so brightly they drown out their entire host galaxies from our point of view, as the brightest objects in the universe. Gamma rays are also emitted by the largest electromagnetic explosions in the cosmos, gamma ray bursts, which occur during supernovae, as well as in colliding neutron stars and supermassive black holes. They release, in just 10 seconds, more energy than our sun will in its entire 10 billion year lifespan, capable of blasting our planet and blitzing all life on Earth, if one occurred in our cosmic backyard. Gamma rays are also emitted when the crusts of the most powerful neutron stars, magnetars, crack and rupture to displace energy, These so-called starquakes have been known to churn out enough gamma radiation to leave a noticeable mark on our planet's ionosphere from more than 40,000 light-years distant. Once again, such an event occurring closer to the solar system would surely spell the end of days for humanity. Thankfully, the nearest potential gamma-ray sources to Earth are all hundreds, if not thousands of light-years away, nowhere near close enough to pose any real danger. But it is nonetheless a chilling reminder of the power wielded by the electromagnetic force, and the four forces in general. Together, they each exert an influence on varying aspects of our reality, dictating our existence and determining the laws of physics. Perhaps one day, someone will find the graviton particle, and will describe its behaviour in terms of the Standard Model to create a championing theory of everything, capable of shedding light on the one true essence that rules our cosmos. Until then, however, we are constrained by the limits of the Standard Model. Though it has gotten us this far, the framework still has many imperfections which remain unaccounted for. And only by answering these questions, in the context of gravity, will we ever be able to get a better understanding of the forces of nature than this. And with that, I bid you good night. C signing out.